We previously talked about what a limit was and how to find a limit. And there are a number of different ways to find limits. We can always just look at the graph, or we can find limits numerically by plugging in values very close to the x value where we want to evaluate the limit. And we can also just look at limits analytically. That is to say, use whatever algebraic properties or even trigonometric properties we know to evaluate the function at that specific point. And the easiest way to do that is to do something called direct substitution. That is to say, we can just directly plug in whatever x value where we're trying to find the limit into our function and see what the output is. And if it's a numeric value, we can often find that that is indeed the limit. The problem is that sometimes we will get what's called indeterminate form. So indeterminate form, I just want to take a moment. I just want to be very clear about what we mean here when we say indeterminate form. So some examples of indeterminate form might be something like 0 over 0 or infinity over infinity. And there's some other unique ones, something like 0 times infinity or infinity to the 0 power or even 0 to the 0 power, even something like infinity minus infinity. And there's a common recurring trend here. Indeterminate form does not mean that the value is undefined necessarily. It may be. It may indeed be undefined. However, indeterminate form by itself does not mean undefined. What indeterminate form actually means is that we cannot determine the value in that current form. And you can see here that most often this appears when we have something involving infinity. For example, something like infinity over infinity. And to be clear here, let's just make sure we understand why. Infinity is not a quantitative value that we can just start counting to. It's not like after 50 years of counting, we finally arrive at the number infinity. Infinity is more of a concept. It's more of a way of explaining or describing that a number is growing or decreasing without bound. That is what it's trying to indicate or refer to. It's not necessarily something that we can actually count to. In the same way, the same algebraic properties that we have don't necessarily make sense. We can't necessarily say something like infinity plus 2 is greater than infinity plus 1. Or for that matter, even plug in infinity. We can't evaluate a function at infinity. Now we can explore what a function does as x approaches infinity, but it's not something that we can directly substitute into a function. And so for this reason, we have a number of different indeterminate forms that are essentially just telling us, hey, we can't exactly determine the information that we want in its current form. We have to do something else. And so what we're going to look at are a number of functions today where we'll be evaluating the limit at a specific x value, and we'll look at what we need to do when we arrive at indeterminate form. Our goal often is simply to use algebra or sometimes trigonometry to create a new function that is pretty similar to our original function, but more importantly, it gives us an equivalent limit. So let's talk about what that means. So first off, what are a couple of strategies we may use? Oftentimes when it's a rational function, we may want to divide out common factors. So I'll just write that, divide common factors. And in algebra, we saw that this was often simplifying the factor. Sometimes we may want to use the conjugate. We may want to multiply the top and bottom by the conjugate. So something like, for example, if you have x plus 4 here, and let's say this is an x down here, oftentimes we may want to just multiply the top and the bottom, the numerator and denominator, by that conjugate. And oftentimes that results in something a little different. And sometimes we may want to use special trigonometric functions, or special trig limits, I should say. And the two most common ones are the limit as x approaches 0 of sine x over x, say that that's equal to 1. And the other one is to take the limit as x approaches 0 of 1 minus cosine x over x is equal to 0, something like that. Okay, and they're obviously the more obvious ones, but this is where we'll start with for now. So let's take a look at a couple of these problems here. Okay, let's start with something like number 1. So first off, let's try to do direct substitution. Again, that is to say, we're going to try plugging in 0 into this function here to see if we can determine the limit as such. And when we do that, when we plug in 0, we get 0 in the numerator. That's okay. But in the denominator, notice what happens. We get 0 times 0 plus 1. Well, all of this is to say this entire denominator just is 0. Now, a quick word of caution here before I talk about this. Do not say that this limit is equal to 0 over 0. Because later on, some of you are already looking at this and you can determine that a limit to this actually does exist. And so we can't say that the limit is equal to 0 over 0 and then later on say that it's equal to something else completely, because that wouldn't be mathematically accurate. So don't say that it's equal to 0 over 0, although that may be tempting. You can just leave it as 0 over 0, or you may even write something like 0 over 0 form, right? But what this indicates to us is, hey, a limit to this function may or may not exist, but I cannot determine the limit of this function in its current form. So instead, what I want to do is I want to see if I can use any algebra to find an equal limit using a similar function. Well, if you're looking at this right away, you'll notice that there's a common factor of x in the numerator and the denominator that I can divide out. So what I can now say is the following, that the limit of this function is equal to the limit of 1 over x plus 1 as x approaches 0. Now again, to be very clear, am I saying that this function up here is equal to this function down here? And the answer is no. They are not equivalent functions. They look really similar. Actually, the only difference is that this function up here has a hole at x is equal to -1. At x is equal to 0, I apologize. At x is equal to 0. Other than that, these graphs look identical. However, they are not exactly the same function. That is not what I'm trying to say here. In fact, what I'm trying to say, or more accurately, I should say, is I am stating that the limit of this function up here, is equal to the limit of this function down here. Not that these two functions are equal, but that their limits are equal. So using algebra, I'm able to come up with a similar function that a function that agrees with the original function, but has an equivalent limit. Now let's try direct substitution. So now I can say equals 1 over 0 plus 1, which is equal to 1 over 1, or just 1. So these equal signs are fine now because I am saying that the limit of this function is equal to 1. Okay, let's take a look at some other ones. I'll run through a few of these more quickly. Something like number 2. Again, if I try direct substitution, I get 0 over 0 form. However, what I could also do is factor the numerator, the numerator is already simplified, but factor the denominator. And I see that there's a common factor of x minus 9 in both, and say that this is equivalent to the limit of 1 over x plus 9. And using direct substitution here, if I plug in 9, I get 1 over 18. Okay, so this actually was pretty straightforward. Okay, let's try something like number 3 here. Now, at first glance, number 3, there doesn't seem to be much that we can do with this. We can't really quite simplify the numerator denominator. We can't even actually use any trig identities just yet. But something that I could do is I could multiply both the numerator and the denominator by 7 over 2. Or excuse me, not 7 over 2, I apologize. 7 over 7, sorry about that. 7 over 7. Well, why would I want to do this? Because this limit is equal to the limit as x approaches 0 of 7 sine of 7x. And if all I do is just move around the 7 and 2, switch these around, look at what I have in the denominator. I now have 2 times 7x. And now I can actually take out this scalar of 7 over 2 to the outside. And so rewrite this as 7/2 times the limit as x approaches 0 of sine of 7x over 7x. And if we refer back to some of these special trig limits, like the one that we have here, we see that the limit of any argument, or the limit of sine of any argument here, over that same argument is indeed equal to 1. And if you needed to, you could temporarily just set u equal to 7x, but I don't really think that's necessary. I think we can see here that we have the same argument for sine as we do in the denominator. So this entire limit here is going to be equal to 1. So 7/2 times 1, we're left with 7/2. Okay? Now, I encourage you to pause the video and try a number of these and check your solutions with what I have. I will briefly actually discuss number 5, Just want to make sure that we're clear here, because this is a problem where we can't really do anything else algebraically. There's not much I can do to simplify. There aren't any trig identities that we can use. But here we notice that it's a left-handed limit or left-sided limit. And so we can really just explore the behavior of this function as x gets closer and closer to 2 from the left side. So what's something that we can try to do here is just evaluate the limit numerically. So try to just do something like 1.999, something that's really close to 2 from the left-hand side. And when we go 1.999 minus 2, well, that's negative 0.001. Well, what does that give us? When we divide something by a very, very small value, our quotient or our output starts to grow and gets closer and closer to infinity. But since we're dividing by negative 0.001, this would be negative infinity. So this limit doesn't exist, but since we're describing we're finding a one-sided limit, it is accurate to say, or possible to say that this limit would just be negative infinity. For something like number 8, if you were to see something like number 8, where if we're told that this function is continuous, we want to determine the value of a. Well, if we know that this function is continuous, that means when x is equal to 2, where this piecewise function is split up, this output would have to be equal to this output. So that is to say, f of 2, we know, is equal to 2 minus 3. We're plugging into this piece right here, which is negative 1. And if it's a continuous function, that means 3x squared plus a needs to be equal to negative 1 when we plug in 2 into this as well, in order for this to be true. So we would say 3 times, what is this, 4 plus a is equal to negative 1. A would then have to be equal to negative 13. All right. Now I want to close the lesson today by actually talking about the intermediate value theorem. The intermediate value theorem, like many theorems in calculus, isn't an overly complicated theorem to digest, but it's incredibly impactful in the ways that we can use it. So the intermediate value theorem says the following. It says, suppose you have a continuous function on some interval AB. So let's just write this out. Let's just say this were A here. Let's just do that negative 1. And let's just put B here at positive 2. And suppose you had some continuous function that was continuous on the closed interval from A to B. So something like this, for example. We have a continuous function on the closed interval A to B. The intermediate value theorem says that if this function is continuous on this closed interval, and there is some y value, which we'll call k. Let's just kind of switch this here. We'll call this particular y value here k. That is between f of a, so we'll call this f of a, and f of b. Then there must be at least one x value. There must be some x value, which we'll call c, that produces k. It has to happen at least once. There must be at least one x value between a and b that produces this k. That is between f of a and f of b. To put it more simply, a continuous function will take on every possible y value between f of a and f of b. And that makes complete sense when you look at this here, especially when you look at the graph. That if the function is continuous on this closed interval, it must take on every single y value between f of a and f of b. So what are some ways that I might ask about this? Consider something like number 9. Well, number 9 says, all right, look at this function. Determine if IVT guarantees a c value for the given interval based on what's given. Well, right away, I see that this is a polynomial function, so this is continuous for all values of x. So that condition for IVT has been met. Now, if that is true, then let's look at, if this is our a, b, this is our closed interval here, what is f of a, or f of 0 in this case? Well, when I evaluate the function at 0, I get 0. What is f of b? So f of 5. Well, 25 minus 5, well, that's equal to 20. Now, ask yourself, is 12 in between 0 and 20? And the answer is yes. Since f is continuous, and this value that we just found is indeed between 0 and 20, between f of a and f of b, there must be a C value or a C value such that f of C is equal to 12. That must be true. IVT does indeed guarantee that. In other words, every value between 0 and 20 must exist between 0 and 5. Every value between 0 and 20, we are guaranteed that every value between 0 and 20 will exist between 0 and 5. Let's try another one. What about something like number 10 here? Well, again, we can try to find f of 0. When I try plugging 0 into this function, I get -4 over -2, which is just 2. Now let's try plugging in 3. F of 3 is equal to 9 minus 4 over 3 minus 2, and that's just going to be equal to 5. Now, is 4 in between 2 and 5? And the answer is yes, that does work. But wait, I'll even write that. Wait, this function is not continuous. In fact, I'll just copy that. You can say f of x is not continuous on 0 to 3 on this closed interval. So the intermediate value theorem doesn't guarantee a C value. Now, had the same problem been given on something like 3 to 7, for example, then IVT would work, because the only place where this function is not continuous is at x is equal to 2, which is within this interval here. So had I given you another interval, then possibly IVT could guarantee a C value such that f of C is equal to 4, because it would have to be between that range, okay, between 2 and 5. Now, the last problem here is to simply ask, find the value of C from either 9 or 10 if 1 does exist. Well, 1 doesn't exist in number 10. So let's just do number 9. So just from number 9 here. So again, this problem here. So we're just looking at, okay, well, we know that f of C is equal to 12. So let's write that. F of C is equal to 12. So that result must be able to come out from this function. F of x is equal to x squared minus x. So let's find that C value. So since we're finding the C value, we're going to say 12 is equal to C squared minus C. C squared minus C minus 12 is equal to 0. C minus, well, I'm getting mixed up with my C's and my parentheses. C minus 4 times C plus 3. So C could be equal to 4 or -3. Now, hold on one second. Remember what the interval was from number 9. The interval was 0, 5. My interval was 0, 5. So again, in this case, since our interval was 0, 5, and that corresponded to an output between 0 and 20, right? The only value that could actually work here in this case would have to be 4. -3 could not work because -3 is not within this interval here. We're finding x values. So the only value that could work is 4. C is equal to 4. Now, the last thought I just want to leave you with is this wording here about the intermediate value theorem, the idea that it has to be a closed interval. And ask yourself why it would have to be a closed interval. Now, the basic answer is that we need a closed interval because if the interval is open, then we cannot determine f of A and f of B, and therefore we would not be able to determine an upper or lower boundary, if you will. If these values here were, well, it looks like I won't be able to quite do it, but if these values were open, then I wouldn't be able to, oh, that's the wrong spot. I wouldn't be able to determine an f of A and f of B, something to compare it to or bound myself. That's on a very basic level. And as kind of a counterexample or something to think about is to look at this function here, right? So I've given you a piecewise function. And so this is an example of something where, ask yourself, is my function continuous from -1 to 1? Well, it clearly is. From -1 to 1, my function is indeed continuous. So on that note, it would seem that IVT should be able to guarantee every single y value between f of a and f of b. But wait, look at this a little bit more carefully. There is no such value between -1 and 1. There is no value between -1 and 1 such that f of x is between f of -1 and f of 1. I'll even write that. There is no value in this interval such that f of x is between f of -1 and f of 1. So just something to think about whenever you're asking yourself why indeed there would have to be a closed interval for IVT to work.